Hi everyone. This last problem turned out to be a little more difficult than I expected, but I think we can still wrangle it, so let's take a look. First, I'm requesting a third-degree Maclaurin approximation for x sine 3x, and I give the hint that you should use the series you already know. So if we're doing that, we take the series for sine, which is x minus x cubed over, well, you know, we're really already done here. We don't need more terms than that. So that's an approximation for sine x. Let's substitute in 3. So that gives us 3x minus 3x cubed over 3 factorial. And then we're going to multiply the series by x. So x sine 3x is going to be approximately 3x squared minus 3 cubed. It would have been x cubed, but I'm multiplying by another x, so that's x to the 4th over 3 factorial. Well, this is already too many terms. This is a 4th degree approximation, so the 3rd degree approximation is just this one. So the answer is 3x squared. Ta-da! All right, but then it requests, what does it request? It says use it to approximate the value in x equals 3, so sine 9, 3 sine times the sine of 9. So plugging in 3, it's approximating that value as being equal to 27. Just out of curiosity, I want to see what it actually is. All right, it's actually about 1.2, so that's way off. But that shouldn't be surprising, because we're pretty far from the center of the series. This is centered at 0, and we're using only one term to approximate it. So yeah, I guess I'm not surprised it's so far off. All right, so the last part of the problem is where it gets difficult. It's saying use the Lagrange error bounds to bound the error of this approximation on the interval from -2 to +2. All right, so that means x could be anything on that interval, and I want to know what's the maximum possible error. So we've got this equation. We know that for an n-degree approximation, the magnitude of the error is given by the n plus first derivative evaluated at z, where z is some mystery number that's between the center, which in our case is 0, and the x value that we're evaluating at. So that could be -2 or it could be +2. Divided by n plus 1 factorial times x to the n plus 1. This is for a Maclaurin series. If it were a Taylor series centered somewhere else, this term, of course, would be different. Okay, so the problem is the method that we used up here to get these coefficients are the result of evaluating nth derivatives at the center of the series, at 0. But we don't actually know an expression for the nth derivatives. So that doesn't give us anything that we can use here. However, I'm thinking, why not try it the hard way? Like, we know how to take derivatives, and I can see that the 3rd degree approximation is actually the same as the 2nd degree approximation. So if actually I'm looking for n equals 2 here, that means I only need to be able to take 3 derivatives in order to find an expression for this. And that doesn't seem that hard, so let's give it a try. All right, so I'm trying to find, so when n equals 2, I'm trying to find the 3rd derivative of my function. So my function is x times sine, of 3x, there we go. So the first derivative, I'll use the product rule, so that gives me derivative of x is 1 times sine of 3x, plus x times the derivative of the sine of 3x is cosine 3x, times 3 because of the chain rule. There we go. All right, first derivative. Let's do the second derivative. So sine of 3x is going to become cosine 3x, and then I've got a 3 out front. And then let's use the product rule here. So derivative of 3x will just be 3 times cosine 3x plus 3x times the derivative of cosine, which is negative sign, so I got a negative out there, 3x, times another 3 because of the chain rule, so I'll just make this 3 times 3. And notice the parentheses are this way. Okay, so I think I'm going to simplify this because I see I can combine a couple of things. So that's equal to 6 cosine 3x, and then that's minus 9x sine 3x. All right, we're doing all right. No disaster yet. Oh, wait, am I done? No, I just wrote third derivative. Haha, that's the second derivative. Okay, third derivative. So do it step by step. So cosine is going to be negative sine. So that's negative sine 3x times the derivative of the inside is a 3. So 6 times 3 is 18. And then let's do this one now. So I'm going to use the product rule again. So the derivative of negative 9x is negative 9 sine 3x. And then plus the derivative of sine 3x is going to be cosine 3x times a 3. And then the negative 9x is still there. All right, so combining all those together, let's see, I've got a negative 18 and a negative 9, so that's negative 27 sine 3x. And then over here, let's see, I've got a 9 times a 3, so that's, again, a negative 27 x cosine 3x. Cool, well that wasn't so bad. We found our third derivative. All right, so using that third derivative now and plugging into this formula up here for the second degree approximation, which is the one that we're using, I've got this third derivative evaluated at z, all of those little kind of smudges are z, divided by 3 factorial times x cubed. Remember, x is in the range from negative 2 to positive 2. Okay. So I want to make this magnitude as large as possible. I could consider x to be negative 2 and try and make this whole term sort of as negative as possible so that the magnitude is as large as possible. Or instead, I'm going to make all these positive and then just consider positive values of x to try and make the entire thing as large as possible. So 27z cosine 3z over 3 factorial, and then 2 is the x value that's going to make this as large as possible. So I shouldn't write equals 2 here, I should write less than or equal to. So it seems like that the largest value, the sine and the cosine, can be as 1. So this will become 27 plus 27 times z. So z is anywhere in the range from the center, which is 0, up to our x value. So our x value could be as large as 2, so that means z could also be as large as 2. So times 2 times 1, so that's becoming 1 here, over, I don't like to write times 1, over 3 factorial times 2 cubed. Okay, so that is, let's see, so 27 is already 3 cubed, and I've got 1, 2, 3 of those. So that's like 3 to the 4th. Yes. Divided by 3 factorial times 2 cubed. All right. So let's divide by one of those 3's. So that's 3 cubed divided by 2 factorial times 2 cubed. And so I'll cancel a 2 out with one of those 2's. So that gives me 3 cubed times 2 squared. That's nice. So that's, what, 27 times 4, which is 108. So 108 is the upper bound for our error, and that's about right, because as we saw, there was quite a lot of error involved. Yeah, I was trying to find the error, so we said it was 27, and the true value, I think, was like I forget what it was. It was less than 3, whatever it was. So actually our error bound, you see, is not that tight. The error bound is way larger than what our error actually ended up being. But sometimes that happens with bounds. Okay, well, that was an adventure. I probably wouldn't ask you something like this, but, you know, you never know. Like, we encountered this in the natural course of things. So I think the moral of this story is you shouldn't be afraid to just keep pressing forward sometimes.